All right, everyone. Let's get started with today's webinar. My name is Scott Schwieger of Combined Cycle Journal. I'm the moderator of today's webinar, hosted by CCJ and presented by E1. The title is Automating Hydrogen Purge to Maximize Power Plant Safety. Definitely a very important topic to all of us, and that's why we've got so many people registered for today's webinar. Our presenters today are Mark Williams. He's the Business Development Manager at Environment One Corp. And also joining us is Jason Justice of J3 Engineering and Consulting. If you don't know Jason, he used to be at Southern Company and NextEra Energy, and was an integral part of the Power Plant Controls Users Group. And he's been a great benefit to the end user community over the years and sharing information and his expertise. So today's presentation will be disseminated to the attendees via PDF after the show is over. We'll have some type of recording as well that will be sent out to you after the webinar. And if you have any questions during the presentation, just send those through to me via the chat, and we will get to those during the Q&A session at about 10 minutes to the top of the hour. And right now, I'd just like to introduce Mark, and let's get this kicked off. And thank you very much for joining.
Yes, thank you for joining us. We're going to go through automating your hydrogen purge process and seeing how we can do this as safely as possible. So we're going to look at what is a remote operator initiated purge system, the benefits of an automated purge system, what we need to know to get started. There's several things that we need to know. Options for automating your purge system, connection points, tie-ins to the generator, what pipes we need and what we're going to use, what we're going to get rid of. And then we're going to talk a little bit about the 7F automation kit that we have developed here at E1 in conjunction with Jason. Jason will jump further into that, the software, and more of the mechanics of how it interacts with our equipment. Then we're going to talk about CO2 and CO2 vaporizers. It's a very important part of automating the system is being able to deliver that CO2 at a reasonable amount of time with the correct process and equipment. Let's go. What is an operator-initiated purge? It's a purge that's initiated directly from the control room at the demand of an operator. This is not an automatic purge. This is something that has to be requested. If we have a fire, we have an event, we have weather coming in, they make the decision, it's all right, let's go. And there'll be two ways to confirm that that's going to happen, and then the process will start. What are the benefits? Same process every time, no matter who does it. Anyone in this room or this audience can do this, and it will always be the same. You get operators in a room, you get 3 operators, you'll get 3 different processes, how this purge can go. None of them may be wrong, but they're not all the same. If there's an emergency, there's no need to send anybody in harm's way. If we have fire, we have weather, we have wind, nobody goes out there. This is completely controlled from the control room. It will speed up the time a purge takes from H2 to CO2 with the correct equipment and processes. Are you facing CO2 purge issues now? This is a common question that happens across the fleet. So we look at how long is it taking to do your purge? Are we looking at 6 hours, 8 hours, 10 hours, sometimes up to 12? We've seen some go to 16 hours and still not have a complete purge. How much CO2 you're actually going through for your purge? You probably estimate you're doing 2 to 3 times the amount of CO2 that you need to actually purge that generator because of losses in the bottles or process and pressures. What are you using? Bulk CO2 or are you using bottles? Are we using liquid or gas? It's very important to understand these things when we get started. Are you using more then 2 to 3 full volumes of gas to purge your generator. We found it sometimes it's up to 6 times the amount, 6 times volumes to actually get a good purge from H2 to CO2. And that's due to losses and practices. You got a way to confirm that CO2 is flowing and how much CO2 is actually flowing to the generator. What's the condition of your CO2 regulators? Are they in good functioning condition? Found many places where they're either in poor condition or they're just not there at all. And we're just cracking a valve and let's go and see what happens. That's why we end up with these very long purge times, 6 to 12 hours. What CO2 purge pressure are you using? A lot of places are using a blanket purge. They're flowing the CO2. What we're going to do is we got to bring the pressure way down to 15 PSI, 12 PSI, and flow at very slow rates to keep from freezing. What we're going to talk about today will advance us past that to bring us so that we can purge at 50 to 65 PSI and flow 6,000 to 7,000 standard cubic feet per hour to the generator. Based on the frequency of your purges, do you feel your operators have a good understanding of the process and are well trained? What we found is that outages are getting spread out further and further between. We're not doing as many outages. We're pushing them to the limit. They keep sliding. So if you're lucky, you got 1 or 2 guys in the plant that can actually purge the generator. They may have only done it 2 years ago. By automating the process, what we're going to do is we're going to make it the same. Always, every time. Okay. Other things we need to know is we're going to look at what you have for your CO2 storage. We need to know the case volume of your generator. That can be found inside the manual of your generator book. It'll tell you exactly how many standard cubic feet that your generator contains and how much gas you need to make the purges. And then going back to hydrogen will give you the same information. We're going to review your purge procedure. We're going to see how you do it now so we can understand where the possible pain points are that could be slowing you down so that we can address those with the right equipment to help you move on. Review the existing PNID. We want to know what's on the existing PNID so we can identify what we're going to use, what we're not going to use, and know the piping and type of generator you have. Then we're going to go down. We're going to review the existing manifold. So we'd look at a manifold like this and all these pipes. We can bring this down in valves. We're looking at probably 7 manual valves plus the automated valves from something like this. In a complete gas station that will do your online monitoring, your purging, and monitor your gases. We'd call this like going in and making this a green field. Cut all these pipes off at the top, take everything up here that's redundant and no longer needed and obsolete, and tie into our generator. Clean pipes all the way down to whichever process that we determine is the best to get us to a purge. Bottle racks. We like to go and review the bottle racks. What condition are they in? Do we need to look at getting new bottle racks? Good hoses, good regulators. All right, there's several options that we have available to do an automated purge. Going a little fast. Remote actuator panel. If you have a manifold, a newer setup that's in really good condition, what we'd opt to do is use this remote automation panel to tie into your existing manifold. As part of that process, we're going to go through and identify connecting points, tie-in points, set up double block and bleed valves on all valves so everything will be isolated when we go through the process of doing the calibration. This also has a fully explosion-proof analyzer that can read all 3 gases. The purge. Second would be a standalone manifold. If you have a manifold that's in bad condition, but you have very good equipment, that's your monitoring equipment for the basis of the generator. We'll take this and put a single analyzer with the actuators, gas for hydrogen and CO2 monitoring with transmitters so that we can monitor this from the control room. And part of this process will be we update software so that you can actually change ranges remotely and know what flavor of gas that you're actually looking at. And this is what we'd call a complete new gas station. So we're going to take out, this is on a Siemens Westinghouse unit down in Florida. What we did is we cut all the piping out. As we look back here, one too many. So this is where we would take and cut all this pipe out. A lot of this is redundant and obsolete at this point when we go to a full gas station model. So we cut this out to what we would call a green field and start from there. Oh, wrong button. Sorry. There we go. So this comes with a complete manifold, manual and automatic spool pieces, rotary actuators for your CO2 in your vent, and solenoid valves to cut off your hydrogen supply on the inside. It says redundant analyzers, so you actually during operating, you have a backup analyzer all the time. So if one goes out, you still have readings. One of them can be set automatically, well, with the new remote range change. When we go to purge, we'll take them and switch them into H2 and CO2 before we start the purge, and then follow the gases. This is a complete new system. What are the options for automating a purge process? Rotary actuators with 4 to 20 milliamp feedbacks or switches, open and close. There's two different versions that we can use. Solenoid valves with check valves. That's part of on the gas station on the inside. We have some solenoid valves for cutting off the hydrogen because we want to make sure that the hydrogen is stopped before we open up vents and start feeding any other gas. Gauges and transmitters, which we add to the gas station so that you know what your CO2 pressure is. You know what in the control room with the 4 to 20 feedback. And also your hydrogen supply gases are the same. CO2 flow meters and transmitter. Part of this process that we're going to use, we'll use an ambient vaporizer, but part of the exit manifold from the vaporizer has a flow meter. So we're going to confirm that we have gas flowing. We're going to confirm how much gas is flowing and what the total gas is flowing. And of course, installed explosion-proof H2 analyzers with remote range change capability. This has become pretty important. In the past, when we first started doing this, we had to have somebody, once the purge was done and we thought, you know, we've flown enough gas, got enough CO2 going, somebody would go out in the field and actually press buttons, switch over to H2 and CO2 to verify that the purge has been completed. But working with Jason, we came up with some ideas and said, why can't we just do this remotely? Is that possible? We get together with our engineering team to make that possible so that we can change that in the control room, monitor the gases. So our tie-in points, of course, is going to be the top header, bottom header, fan pressure and suction lines for your online monitoring so that we can return the gas to the generator and we're not always venting gas. CO2 supply line, hydrogen supply line, vent line, very important, and an H2 analyzer connection at the vent line so that we know. We want to read what's going out of the vent during this process, not necessarily what's in the case, because the vent's going to tell us once we hit that stratification and we start moving into CO2, then you see the numbers drop. Okay, we're good now because we've confirmed that. We'll be using an analyzer, a 4 to 20 differential pressure transmitter, so that we know we have flow again across the analyzer. We're going to use the flow totalizer and flow rate from the CO2. So we're going to have 3 to 4 different points when we go through this process to confirm that we actually have a good, clean purge and a safe generator. Kind of an example of a gas station. This one actually happens to be the remote purge. Just lost my train of thought. As we call it, the ROI. This is if you had an existing manifold that was good. We'd add our vaporizer, the ROI, and just type into the H2 and the CO2 systems. So now we're going to talk a little bit about the 7F Purge kit and what that's all about. It comes with enhanced DHCP Purge software and electronics. So we're going to have all those new features of changing the gas ranges, alarms, and flow rates. All of that's going to be part of this package. So we have remote change from H2 and air, as well as we've developed lately in the last year, remote range change from H2, from CO2 back to H2. It's a new process. Be a stainless steel marshalling box for the new connections for the rotary actuators that we're going to install. Indicating transmitter for seal oil system. Part of this process is we're going to take the generator, trip it, it's going to come offline, we're going to drop the pressure down, just call it, we'll start at 30 PSI, we're going to drop it down to 10 PSI, we're going to sit, we're going to stratify a little bit, then we're going to pump it, open up the CO2 line and repressurize it. None of this can happen without the generator getting down to turning gear speed. So there's a lot more that Jason will go into on the software and its functionality, so that we make sure we make a safe transition and we're not jumping the gun and introducing things too soon, pushing CO2 in and H2 out of stack without things at turning gear speed could lead to stack fires from static electricity. So we need to make sure we don't do that. And that's part of the monitoring that we add in the system. We're also going to do 3 Shishek DX actuators with 1-inch ball valves. And I'm going to go over where those go in the collector house and the mounting hardware. And 2 larger 2-inch Shishek actuators with mounting hardware. All right, here's the pictures. So, let's see if I can get this to... Oh, that's not working. Doesn't work. Up at the top right-hand side, you can see one of the actuators for the hydrogen line shut off, to shut the supply line off. And then there's a second one. This way we have 2 points of verification that hydrogen is no longer flowing when we do a purge. Especially in an emergency, that's the most important thing that needs to happen. That hydrogen flow needs to stop immediately. And down on the bottom here, you have the large actuator is actually on the vent valve going out the stack, and the smaller one on the lower right is the CO2 feed valve. The latest thing we had talked about going from H2 to CO2 and then CO2 back to H2, we've added another valve over here on the left-hand lower left so that we can look at the top or the bottom header pipe as we feed the gas through. You can also see down here on this right-hand picture, there's 2 stainless steel tubing pieces in there. That's for us to pick up our samples, going back to the 2 analyzers. There's the word for it. This is an example of the screen that Jason's going to go through here shortly. The purge screen where you have your analyzer 1, analyzer 2, where we're measuring your turbine end and collector end, casing percentages, your actuators open and close over here on the left-hand side, and your standard monitoring screen. And we have an emergency process that Jason will talk about as well, where you can actually hit a button, just start dumping hydrogen, and then pumping CO2. And there's a process behind that that Jason will go into in more depth. We can initiate the purge. We can do an initial vent if we just want to drop the pressure of the hydrogen down because we think something might be happening, like down in Florida where we have hurricanes coming through. Do we want to go all the way? Do we want to wait? Also going to be, where's my seal oil? All right. That's right.
CLODP.
CLODP, we have that up there as well. And then you're going to have your H2 supply open, your vent open and close, CO2 open and close. And then this process that we do is called a pressure purge. It's a lot different than the old blanket purge where you sort of flow gas in slow because we had freezing problems and other issues. So we'll do the pressure and relief. We'll do that process 3 times to make sure. And after the 3rd time, the operator's not happy with what they've seen purged. They don't think it's good. They have the option of doing an extra purge. The expert will take care of that later. All right, here's one of the biggest issues with purging generators, is CO2. Every time we do this, those bottles freeze. The bottom third of all your CO2 when you're using gas is going to turn into dry ice. So you're losing that much CO2. So if you take that across, when you're doing 18, 36, 40 bottles of CO2, you're using 3 to 5 times what you need. So we want to fix that. So when the vapor of the cylinder is reduced, it causes the liquid to change to a gas. We're boiling off liquid and pushing gas out. Get equilibrium back, some kind of energy. That energy has to be taken care of. And that energy turns to cold. It needs heat. We can't get enough heat to keep these bottles from freezing. When dry ice is formed, we're going to lose 30 or more % of each bottle on a gas purge. You can see where the bottom part of the bottle there is frozen. I've seen them, and everybody's seen the hoses. You're out there with a hose. All you're doing is washing the frost off on the outside of the bottle. That's a solid block of dry ice in the bottom of that bottle. Looks good, but it's not really helping too much. So during a purge, when we use the vaporizer I'm going to talk about, we want to use liquid. And this is why we want to use liquid. So with liquid, we're only going to lose about 10% of the bottle because the siphon tube's not deep enough to hit the bottom of the bottle. So what happens is to open up the valve, the pressure in the top is going to force liquid up through the siphon tube. We get a higher flow rate and a higher amount of CO2 that will actually get to the generator. This is a key thing. So when we change these new systems, we got to go from gas to liquid. It takes less energy to push liquid out of that bottle and helps reduce the freezing. So what we use on our systems and we recommend is a turbidol, non-powered vaporizer, which you can use with liquid dip tube CO2 bottles, or you can use with a bulk tank. What you're going to have your liquid CO2 coming out of there. At its first stage, it's going to be in that bottle somewhere between 800 and 1100 PSI. We're going to drop that down to about 400 to 350 PSI. Then we're going to send it through the centerpiece, which is a liquid conditioner. goes into the tubes, goes up into this tower. This tower is about 4 feet square by about 12 feet tall. So at the front of this, you touch any one of these pipes, you're going to get freeze burn. As it goes through this tower, you'll eventually see it get to the end and there'll be no frost built up on there. So you can grab a hold of that pipe and it'll be the same temperature as the outdoor temperature. So it's not going to hurt you. And that's how we achieve the flow rates. And the way these are designed, we look at the latitude, longitude, location of where it's going to be installed. Is it going to be installed outside? It's going to be indoors. Then we go and hunt down the mean low temperature expected across the year. That calculation is taken to size that vaporizer tower. So once now over here we got gas, we now have relief valves all over the place for protection. We have an air actuated valve to keep it. So if it starts running low, and I think Jason saw that on one of the last purges, we started running low on gas, it'll open up the circuit and bypass so that we're not ever feeding liquid through the system. It'll slow the process down to make sure we have flow. And also we don't want to blow out the CLO system as well. Up there is right in the center is the flow totalizer. That has a 4 to 20 out that gives you what's flowed, total flow, and that all gets recorded back to the DCS room. And then from there, right to the generator. Box thermal is what we use. Fast egas Purge non-powered vaporizer. Designed to ensure gas phase delivery without the concern from forming dry ice. True hands-free system. You don't have to touch this. This is all done in the control room. Flow rate and total flow indication from the box thermal. We deliver the pressure control at 40 to 60 PSI. And this is an example of a couple of installations. You can see one over here on the left with a bulk tank. This is a micro bulk tank. That's got some information on it so it can feed back to say, I'm getting low. You will lose some gas on these micro bulks. They do blow off on occasion to equalize pressure, so they have to be monitored. And if you look around, you can see all the pressure relief valves in different places. They're scary when they pop off when they're standing next to them. Make people jump. And of course, the racks, there are 2 different actuators. This one actually is one system that we put in. That's a smaller, much smaller system on a smaller generator down in Mississippi. But that has all the control to make sure we maintain steady flow of gas. And then down here, you can see our liquid conditioner section. There's my regulator panel. Not a good picture with the regulator. And the regulator panel is over here on this side. We ran into some issues down in Florida where we had liquid CO2 bottles that had metal particulate in it. So working with air gas, we came up with a solution to add filtering to these systems to reduce that occurrence, because it came down with, we don't think the system's working. And then after the investigation, we took things apart. The regulator was filled with a palm full of ground steel. So that's been added. It's a continuous process to look at things, and now everything is no longer copper, it's all stainless steel. Just try to standardize and make best practices improve where we see we need the improvements. That's it. Send your questions. Jason, it's all yours.
Thank you, Mark. Once again, my name is Jason Justice, and I've been fortunate enough to work with E1 for about 15 years now, working on this product and helping it, grow and evolve to where it is today. Now, one thing I will say about E1 is they've been very good to work with and to hear the customer's responses and then to make adjustments accordingly. Let's just jump right into it. All right, so just to give you a little background and history of, how we got to this point. the DHCP cabinets were put on a lot of machines throughout, starting in the late 80s, throughout the 90s, 2000s, et cetera. So there's a lot of E1 DHCP cabinets available out in the plants, right? They were a good system. However, there was a couple of vulnerabilities with them. To start with, the analyzers that you see up at the top right, they were only set up to monitor hydrogen and air. So you had 1 4 to 20 from each of the analyzers, and that's all that they were able to monitor, hydrogen and air. Well, that's great while you're running, flat out on the machine, right, when you're making power. But when you're getting into the maintenance operations of the machine, purging in particular, and you go to purge and select, like, hey, I want to be able to view what the hydrogen to CO2 concentrations are in the machine, or for the air and CO2 concentrations in the machines. And the control system, which was monitoring the hydrogen and air purities, it went dumb. So working with E1, we made some changes to the firmware of the DHCP cabinets to be able to provide the control system the information that it needed to change the ranges. So then you can view not only locally what the purity concentrations are for hydrogen, CO2, and air and CO2, but it was also shown inside the control system. Big advantages. And that was very vulnerable in the purging process initially because the control room operator went blind as to what was actually going on with the purge. All right. So this is how some of that was possible. So going on a little bit further than that, so not only did we work on the firmware of the DHCP cabinets themselves to be able to determine, what gas we're actually monitoring, we went a little bit further to say, okay, well, the control system can now take the place of the operator that was needed at the front of the panel to make those changes for the system when appropriate, right? So what you see in the top right-hand corner is the card that made that possible. So the control system can close some relay outputs on it and then tell the cabinet what it indeed needs to monitor, right? Whether it be hydrogen CO2 or air and CO2, depending on where you're at in the purge process. James. Okay. Put the rest of these up there. Now, Mark went over a couple of these enhancements that we have done with the systems. So not only with the DHCP cabinets or the GGAs is monitoring purity, right? But we also made some changes and some enhancements to the system itself. So the original solenoid valves that were provided were being changed out to MOVs. We've also installed a flow meter to monitor the flow going through the analyzer out the vent. Initially, all you had was a couple of rotometers, mechanical rotometers in the front of the system. Now with the installation of the differential pressure transmitter, we can actually see if we've got good flow going through the analyzer or not. So you can believe that, hey, you're not just reading a static value. And then Mark touched on this as well, as we installed a couple of solenoids to be able to take the sample from the appropriate header, whether it be the top header of the generator or the bottom header of the generator, based off of what flavor of gas that you're purging to and from. And then we added another MOV vent valve to be able to vent from the bottom of the machine. And that is, all these are especially beneficial for the operator-initiated purge process. Okay. So this is a picture of an installation to where, some of the equipment is installed from. A lot of you may recognize that this is a collector cab of a 7FA or 7FH2 generator that's coupled with a 7FA machine, where you see the DHCP on the right-hand side of the picture. I'll figure out how to do this pointer, maybe. I can't figure it out. I'm not smart enough. All right, and then you also see the yellow actuators. So 20HH1 and 20HH2, those replace the Clark Cooper solenoid valves that were originally installed on the machine. With the MOVs, the control system can actually open and close. You can also get feedback via the MOVs to whether it is indeed open or closed, right? And that gives you 2 points of shut off to make sure that the hydrogen is indeed shut off from the machine when appropriate. And then you see the SV1 and SV2 solenoid valves to be able to take the sample from the appropriate header, like we were talking about. The DPT-201 is a differential pressure transmitter that we installed to monitor if we have good flow going through the analyzer. And then you see 20GK2, where that's the venting from the bottom of the
Jesse.
Stop with it. The only thing that's working is the arrow.
Appreciate the effort, Nabila. Thank you. It's not just me. All right. That's all I want to tell you about that. So these are the sample points that are, this little compartment is located up underneath the collector cab, and where you see 20GK1, which is venting off of the upper header of the machine, and you see 20PM1, the little yellow actuator there in the middle of the screen. That is a CO2 supply, MOV, and then SV1 and SV2 to where they actually tap into the upper and lower header. Now, another thing about these systems, automated purging is great, but we also do not want to take away any manual operations that the plant has. So this is an add to, not a take away from. So if any plant still wants to do a manual purge, they still have the ability to do that via all of our installations. Not only for the 7FH2 machines on the 7FAs, but also for any steam turbine generator that we do. I've already talked about that. I think I've hit all those. And again, this is a picture of the screen that we utilize. Okay, so some of the features associated with the operator-initiated purge system itself is there's several different modes that can be utilized, right? What we typically mainly do is a maintenance purge. We're not always in emergency condition, but we also find ourselves in the need to purge the machines, right? From like a maintenance outage, say we just don't want to leave hydrogen in the machine and we want to purge it to CO2 and have our maintenance outage for several days, right? Or if we were doing a little bit further and going to air inside the machine, then we want to, be able to do that. It's not an emergency condition. We have time to purge the machine. We want the system to purge itself. Though we can use it from an automated standpoint, it's not an emergency. So you can gain some synergies associated with that. Like during a maintenance purge, we can pay more attention to the seal oil system. We don't want to outrun the seal oil system and run the risk of admitting oil into the generator frame. So during a maintenance purge, we use the control system and the instrumentation that we put on the machine to help monitor for that, right? And I'll give you an example of that as we go. And during an emergency purge, though we care about the seal oil system, is not as important as getting the hydrogen out of the machine as fast as possible. So we kind of overlook the seal oil system a little bit during that process. During the maintenance purge, we can also mitigate the freezing associated with the CO2 emission. Even though the ambient vaporizers are great and they help a lot, the process itself can be leveraged to help mitigate those concerns. So we use a pressure purge, like Mark was indicating, to where we have an initial high flow rate as we're venting and admitting CO2 to the machine. But as pressure builds up inside the machine, we gain a lot of good stuff from that. You get a high flow rate, and then as pressure increases inside the generator frame, that flow rate slows down a little bit. Then that gives the opportunity for the machine to do a couple things. One, the two gases to stratify inside the generator. The generator was designed to be a pressure containment vessel, right? So we're leveraging the fact that that pressure containment vessel can let the gases inside the generator stratify. And you really want to vent out the hydrogen from the top of the machine, emit CO2 from the bottom. And during that time, as we're emitting CO2, we give time for the gases to separate inside the generator, right? Which helps us from a purge time standpoint, and it helps us from a CO2 freezing mitigation standpoint. Let's see what else. We've actually monitored this at several different sites to where we found that we used less CO2 than typically done from a manual purge, about 30% less, depending on the site. The system itself integrates with what you currently have. Whether you've got a GE Mark flavor control system, whether you've got a Siemens T3000, Ovation, et cetera, we're not adding an additional PLC for your staff to have to take care of. We integrate it with the equipment that you already have. And then we get the ability to remote monitor, whichever flavor gas concentration is needed at the time. There are also some interlocks associated with that to make sure that as you're running, you're only monitoring hydrogen and air. So there's not a chance for the operators to, click a button and then monitor something that they shouldn't be monitoring while the machine's running. Let's see. Oh, so with our, installations of our solenoid valves for our sample points, we can, continuously monitor purity and flow of the DHCP. Okay, and the venting thing, Mark touched on this just a little bit. Like, say if you're going into an outage and you just want to, replenish the hydrogen that you have in the machine, but you do not want to emit CO2, we have a vent feature to where you can bleed the pressure in the generator down and just let it sit. And then at the end of the outage, press it back up with fresh hydrogen if you would like. Okay, so I'm gonna break from that for a minute, and this works. If technology will help me a little bit, I'll give you a little demonstration of the system working, right? So we've got a couple of different modes associated with it. We've got a hydrogen CO2 mode and a CO2 to hydrogen mode. We also have an emergency feature or not. So right now we've got selected hydrogen CO2. The first thing that we do is we select operator initiated purge. We get a confirmation window that says, hey, I indeed want to shut down and purge the generator. I select OK. The first thing that happens is my hydrogen supply valves go shut. You see that here in these boxes as well as in this graphical display up here to the top left, right? The next thing that happens is the vent valve opens up, which is 20 GK1, and it bleeds pressure down in the generator down to 10 pounds. The reason that we selected 10 pounds is because we've got a float trap that we've got to worry about with our silo system. And we do not want to back oil up into our generator frame. So we want to keep that float trap pressurized enough to where draining back to the tank is not a problem. So once it gets down to 10 pounds, the upper half vent goes closed. There's a small pause, and our CO2 supply valve is going to open up. There it goes opening, right? During this time, we allow the CO2 to be emitted into the generator frame to press the generator back up, right? During this time, we're allowing an initial high flow rate of CO2, but we're also allowing time for the gases to separate from one another, right? Because as pressure builds inside the generator, then the flow rate is, slowed down a little bit as pressure builds in the generator. So we're going to get up to approximately 28 pounds, and this is dependent on the volume of the generator that we have, where we actually stop at. Once we get up to 28 pounds, then the CO2 supply valve goes closed, and then the upper half vent, the upper header vent is going to open back and then bleed pressure back down. And this is going to complete at least 3 times. At the end of the third cycle, we're going to get a little pop-up here that says, hey, I need to verify that the analyzer is set up for hydrogen and CO2. The control system with the installation of the remote range change feature, it's going to make that change for us. Now, that's just saying that, hey, I'm at least at that point going to change what flavor gas I'm monitoring to hydrogen CO2. The operators can do that before that if they would like to. I've seen that to where some operators like to see the hydrogen purity go down before they make the swap to hydrogen CO2. They like to see the hydrogen and air purity go down. And that's, it's, 6 one way, half a dozen another. At some point in time, we do need to swap over to hydrogen CO2. So if you have not done so at the end of the third cycle, the control system is going to do it for you. So let it do its thing. So right now we're pressing the CO2 back up in the machine. Our 20 PM1 valve is open, and we're going to go back up. Okay. All right, now, because we're doing a maintenance purge, if we were to happen to see a low seal differential pressure, because we haven't done maybe the maintenance that's been required on our regulator, and we start saying that, hey, we're outrunning it for whatever reason, right? I'm going to give you a demonstration of that too. We haven't seen that in practice, however, that doesn't mean that it won't ever happen. So there's controls that have built in to pause the system, you know, during the times to when the regulator is not able to keep up, to allow it to catch up. So I'll show you that now. So this is a demonstration of when the seal differential pressure goes low, we get an alarm saying that the purge paused because of low seal DP, right? So at that point in time, the valves close and it gives time for the system to catch up with itself. This is only active during the maintenance piece of the purge. During emergency purging, we don't look at that, right? But because this is not an emergency and we do have some time to do this, you know, in the best appropriate manner, we can add these features to make the system behave even better and to, you know, warrant against problems with our seal system. I'll let that go back. We'll reestablish our seal differential pressure. Then after a small pause to where we confirm from the control system that our seal differential pressure is in good shape, it's going to pick itself back up. There it goes. So upper header vent opens back up and it's going to continue back into the process from where it was. Right? Now, at any point in time during the purge, the operators could select off and then all the valves shut and the system be waiting for a next command. However, it'll always try to do 3 purges. So if you were to select off and then you select on again, the control system is going to try to do those 3 cycles again, right? That's just from a fail-safe standpoint. It's not going to sit there and try to track, hey, this time I did, you know, a purge and a half or a cycle and a half or 2 or any of that. The standard is going to be at least 3 if activated. CO2 supply valves opening up. We're going to press ourselves back up to 28 pounds. You know, another part is, you know, the SV1 and SV2 solenoid valves that I showed you on the slideshow. The control system selects the appropriate solenoid valve to monitor which header it is supposed to. So that's this, you know, feedback right here, where you're actually got the upper header solenoid on, and it's seeing, you know, that, you know, based off of our differential pressure transmitter, that we've actually got flow going through the analyzer. Now, you might have noticed that a little pop-up came up in the middle of the screen. What this indicated was that the analyzer was set up for both the turbine end and the collector end to monitor hydrogen CO2, and it confirms what the actual purity concentrations are on each one of those analyzers to say, hey, I'm either greater than 4% hydrogen CO2 purity or I'm not. That's what it determines. So let's say for whatever reason that we didn't quite make it to 4%. Then this extra purge feature becomes available. You can select on and it will do another cycle. So it does at least 3, and then it waits for the operator to determine, hey, am I done or am I not done? So the thought is the control system's giving the information to the operator for them to make the best decision that they need to make. So with this extra purge cycle, it'll do another one. If they want to do another one after that, then they're free to do it, right? Usually what I see is that the operators do the 3 automated purges, and then they'll do 1 more for good measure. We're typically at where we need to be concentration-wise after the 3. let it get back up there, and then I'll demonstrate another mode of the machine. All right, so now we're back to, hey, we're complete with our cycles. Now we can either do another purge cycle or we can select off at this point. I'm going to select off. Okay, so that is the maintenance piece of the operator initiated purge, right? I'll now demonstrate the emergency piece. So for the emergency, we got these two buttons up here at the top. We select emergency on. We confirm that is indeed what we want to do. And then we select on again. Okay. So here you might have noticed that we've got a couple of timers that came up aboard, right? Now I've shortened down the amount of time for demonstration purposes. During the actual emergency condition at the plant, we would want to at least admit CO2 into the machine for 30 minutes. That's the first check, right? That minimum amount of time. The second is we're leveraging our differential pressure transmitter associated with flow and our purity concentrations of our analyzers to verify that we're in good shape, purity-wise, to say that, hey, we've indeed flowed, I don't know if that's a word or not, flowed enough CO2 in through the generator to say that, hey, we're in good shape. Right. So we'll let it do its thing. And those times would be, like I said, a minimum of 30 minutes that we're admitting CO2. I shortened it down for 3 for demonstration purposes. And then halfway through that, at a minute and a half, and in the plant, since it would be 15 minutes, we'll see that, hey, that the analyzers are indeed set up for hydrogen and CO2. Oh, going Trump there. Hydrogen and CO2, and that the concentrations and the flows have to stay good for a continuous 5 minutes time. And that gives the confidence back to the plant that, hey, we've flowed enough CO2 through the machine, and we verified from a purity standpoint and a flow standpoint that we can believe the readings that we're getting, right? At said point in time, we're not quite finished, right? So then you start thinking about, well, I've purged the machine now. How do I want to leave the system? Well, if you leave, no pressure inside the generator for an extended period of time, you run the risk of, backing up oil into the generator frame because our float trap can't maintain a level. We don't really want to leave the machine like that as we're purged, right? So what we do in this instance is once we verify that, hey, we've flowed enough CO2 through the system, we verified that the purity concentrations are where they need to be, we're going to close the vent valve, and then we're going to allow CO2 to continue to flow into the machine until it reaches 10 pounds. At said point in time, we're going to close our vent valve and leave the machine bottled up with 10 pounds CO2. That will help us mitigate the oil intrusion of the seal oil system into the generator frame, right? We'll see that here in a minute. So our upper header vent just closed. We've left our CO2 supply valve open. Now we're building pressure back in the generator frame. All in an effort to mitigate the oil intrusion seal oil system. Then that's it. It's going to sit there and wait for another command. All right, so we've demonstrated the maintenance purge. We've demonstrated the emergency purge of the system. So now I'll show you, and I may be running out of time, probably am, but we'll say, hey, I want to go back to hydrogen, right, at the end of my outage. So I select my CO2 to hydrogen, and just like with our, maintenance purge from hydrogen to CO2, I'll be able to go back to hydrogen. All right, so in this process, we're adding a few more little steps to use our analyzers as much as we can to verify what we actually have inside the machine. The first thing that we're going to do is leverage our differential pressure transmitter along with our purity readings to monitor how much air and CO2 we have inside the machine. It's going to sit and do that for 5 minutes, verifying that the concentrations coming back to the control system indicate, hey, that our concentrations for air and CO2 are in good shape. After it times out, and you see that, from these, number 1 and number 2 analyzer readings up the top, that both number 1 and number 2 are okay. After it times out, then it's going to go check for our hydrogen and CO2 concentrations. Prior to doing that, it's actually going to admit some CO2 into the process. That way we know that we've admitted CO2 into the generator. We verified from our analyzers that, hey, our purity concentrations are good shape, not only from air and CO2, but also from a hydrogen CO2 sample. And we're leveraging our differential pressure transmitter to verify that the flows are going through our analyzers and we can actually believe the readings coming back from them. All right. So after we're happy with the hydrogen and CO2, then we're going to start, doing the process kind of in reverse than what we did with the maintenance purge from hydrogen and CO2. We're going to be venting from the bottom of the machine and emitting hydrogen to the top of the machine. We're going to do that cycle just like we did with the hydrogen and CO2 maintenance purge cycle, and we're going to do that 3 times. And at the end of the 3rd cycle, just like with our maintenance purge, we give the opportunity to do an extra purge cycle back to get our purity concentrations to where they need to be. And that's kind of how it works.
Okay, Jason, thank you very much for that. I think now we're going to open the floor up to questions. Scott?
Yes. All right. Thank you, Jason and Mark. Everybody can submit questions into the chat sidebar. There's a little icon down at the bottom right that you could access and send in your questions. And while we wait for some more to come in, we'll start with one for Jason. Jason, will the MOVs function on loss of power like the old solenoid dump and purge valves?
So no, we wanted them to fail in place. We did not want any spring returns because then you start getting into a back and forth as to what's actually fail safe. So what we determined is it would be better for them to fail in place. Right? However, if the MOV was to fail in service and it was being given a command, whether it be to open or to close, we've got some logic inside the control system that monitors the amount of time that it gives the command to where it sees the limit or the feedback coming back from the valve to give the operators an alarm indicating that something's wrong or not wrong. But no, they will actually fail in place from loss of power.
Okay. And what is the effect into the generator if the degassing process is too fast? And do you have any recommendations for specific duration of the degas process?
The degas process really depends on the amount of CO2 that you're able to admit to the machine as well as the size of your vent. What I typically see on vents of 2 inches to 3 inches is it takes about 5 minutes to vent the machine down to say 10 pounds. And depending on the CO2 pressure supplied at the input of the generator, typically takes about 15 to 20 minutes to press it back up. So with those instances, and we've done a lot of them now, it usually takes about an hour to hour and a half to do a purge on the machine. And that is, a lot better than, some of the things that Mark was talking about, 6, 8, 10, 12 hours. However, it's not so fast to where you're actually shocking the generator.
Thanks. You answered about like three other questions in that one answer. So
That was my plan.
so, can you demonstrate how the removable spool pieces work with this system?
I can't demonstrate it with my, my simulation, but what I typically see on the 7FH2 machines with the GE machines is that the spool pieces are located. Let's see if I can show this here. Go back a little bit.
Deep inside.
They're way up in here. My mouse isn't really. So what was originally supplied is very hard to get to. Matter of fact, if you get them out, chances are when you put them back, they're going to leak. So what we've been recommending is that these spool pieces be relocated to outside the collector tab. There's a couple of different, systems that we have done to where you actually can put in like an interference fit spool piece to make sure that, hey, you've got the appropriate spool piece out to go to, say, air, but at a minimum, relocating them from where were originally provided to outside the collector cab is a big time for everybody involved. But we don't have any automatic removing of spool pieces.
Okay. Does the system meet regulatory compliance with NFPA 853 or IEEE 980?
Well, you'd have to show me those because I don't remember the codes, but yeah, I mean, what we're actually looking at is the amount of CO2 that we're able to flow inside the machine. So we're able to track via a flow totalizer the total amount of CO2 at the beginning and the end of the process. And even better than that, we're actually looking at the differential pressure associated with the flow going into the analyzer. And then you have your two purity readings, right? So we're 100% confident that we have the appropriate amount of CO2 that went into the machine, and we're monitoring what the gas coming out of the machine is via our analyzers.
Scott, hold on. We have a question
Yeah.
from live inside E1. So hold on just 1 second.
If you lose the power, how does the vaporizer react?
Vaporizer does not need power to run. The only thing that we suggest you do is take the flow totalizer and connect that to critical power so that you can have a reading there. But if you went completely black, the system will still purge the generator without any need for heat or 460, 480 power to get that liquid and turn it into vapor. Yes. And the analyzers are all going to be hooked up to critical power anyway.
Yep, and the valves are being powered by UPS power as well.
Yes.
That way you're confident that you can move the MOVs as you need to move the MOVs. Some other systems that are out there in the industry require a 480 watt heater, a 480 volt heater, which is a potential vulnerability if you were to lose power.
The idea with the sizing of the vaporizer is to make sure that we can meet that 1 hour to 2 hour time range, because at that point, that's where your UPS or battery backup is going to run out. And we want to make sure that we get that hydrogen out before we lose the seal oil system. And we know what happens when hydrogen comes out of cross brushes on turning gear. Not good things. So that's the target of this whole process, is increased safety, risk mitigation, reliability, and giving you the most robust system that we possibly can. And it takes two of us to make this happen, along with our full engineering team. I will say that the Shishek valves are rated for the area. The valves, the actuators and the valves are rated to the fire codes.
Now this system is an operator-initiated purge system, so 9 times out of 10, we do indeed want the plant to initiate the process. However, we can work with you if you want to do something automatic too. Like for instance, say you lose critical power on your machine, your seal differential pressure starts sagging. Well, what we don't want is for that gas inside the generator to be venting out the seals at the two ends. That is a potential terrible day for everybody. So we would rather initiate the purge. But some plants want to do that and some plants don't. We leave that up to the plant to determine, how they want to respond to those particular conditions. However, we do put on enough instrumentation to understand what's going on with your silo system to help you make that decision.
Okay, thank you so much, gentlemen. That was a good note to wrap up on, but a question did come in that I think that Jason would like to answer about the MOVs, and then we can wrap up. If the MOVs did fail on the vent system, maybe 20 GK-1 or 20 GK-2, is there a manual override to continue with the purge, or would you maintain the manual purge valves to continue?
Yeah, we always maintain enough manual valves to allow you to effectively, do a manual purge on any system that we put in, whether it's on the gas turbines, the 7FA like we demonstrated here, or for the steam turbines. So we don't want to take anything away from the process. We're adding to. So if you were to say fail, and we haven't failed one yet, in I don't know, probably the decade that we've been doing this, we haven't failed one yet in service. However, if it was to be failed in service, then yes, you do have the ability to conduct a purge via manual means and manual ball valves. And the actuators themselves, they do have a manual override on them, but it's not super great either. It's a little Allen on the top of the actuator that you can spin and spin and spin for, minutes and minutes and minutes to get it to move. So the effective way to do that would be to use the manual ball valves that you have in place to isolate the MOV.
All right. Well, thank you so much. There are some questions that were left unanswered, but the E1 team has to get back to their training sessions today, and we're going to provide those questions to Jason and Mark, and they were going to get back to everyone with detailed answers to your questions. Once again, we'll be sending out some version of the presentation to you very shortly, probably within the next week. And we would like you to continue to engage with the Combined Cycle Journal and E1 and J3 Engineering and Construction. Thanks so much for joining us. Thank you, Jason. Thank you, Mark, and the team at E1. And once again, my name's Scott Schwieger, Combined Cycle Journal, and we'll see you next time.
Thank you all.
Thank you.